right, so we are doing the semester 1 midterm review for Algebra 1. So starting with number 1, we are going to be labeling a graph based on a situation. So Sarah rides her scooter to her neighbor's house to babysit. After babysitting for 2 hours, Sarah's neighbor drives her to a mall to shop with the money she just earned. After shopping, Sarah's neighbor drives her home. So we want to sketch a graph to represent Sarah's distance from home over time, and we're going to label each activity. So when you are labeling the activity, you kind of have an option. You can either number it up in the problem itself, or you can write the list out at the bottom. But starting with this, because they tell us we are sketching a graph to represent her distance from home over time, we know that her distance from home is going to depend on the time. So that means time is our independent variable, which means it is our x-axis. And then distance is our dependent variable, so that is our y-axis. So going through the story, we start off, Sarah is at her house and she's riding her scooter to a neighbor's house to babysit. So that means her trip would be increasing, her distance from home would be increasing over that time. So then she gets to her neighbor's house, and then she has to babysit for 2 hours. So since she's babysitting, her distance from home isn't changing, but it is going to be continuing with the time. Then once Sarah's neighbor returns, they go to the mall. So because they're going to the mall, we can assume that she is going farther away from her house. So again, we're going up to increase that distance. And then after shopping, well, if she's shopping, that means she's going to have to be spending some time at the mall. So we're going to have a little bit of a flat line. But then her neighbor drives her home. So then if she's driving her home, it just comes all the way back down to home. So when you're doing this, I used colors to kind of label what was happening. But you can use numbers, letters, colors, kind of up to you how you want to label it. But just make sure it's clear what is happening in each section of your graph. So then for number 2, we have a table that shows the relationship between the number of students at a pizza party and the number of pizza slices remaining. So first we want to know if the function is linear or nonlinear. So looking at this, my independent variable is just going up by 1 every time because it's 1, 2, 3, 4, blah, 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 blah. But my pizza slices remaining, first we would lose 2. 14 to 12, that's another minus 2. Then we are losing 2 more every single time there's another student that comes. So because this is a constant rate of change, this is linear. So then, to represent this relationship using words, we can say that they're starting with 16 pizza slices. 16 slices. 2 slices were eaten per student. Or something along those lines. Something to just indicate that we were going down by 2 with every student that came to the party. So then, to represent the represent the relationship using an equation, think of something like y equals mx plus b, because the b is wherever you start. So in this case, we start at 16. And then my m would be our rate of change. So because my y value is going down by 2 every time, it's going to be negative 2. So then we would have y equals negative 2x plus 16, and then you're done. So for 3 and 4, we just want to decide if it is linear or nonlinear. So with number 3, we're going up by 1 every time with the x values. And then with the y values, we have plus 1, 1 to 4 is plus 3, 4 to 9 is plus 5. So you can see that this is not the same number every time, so this is nonlinear because it does not have a constant rate of change. Okay, so then for number 4, looking at it, our x values go up by 1 every time. And then our y values, we go 1 to 1.5 would be plus 0.5. 1.5 to 2 is another plus 0.5. 2 to 2.5 and 2.5 to 3 are all plus 0.5. So because they have the same rate of change between the x and the y values, this is going to be linear. So constant rate of change. So then for number 5, we have the function a equals 2n plus 3 represents the amount of money made from selling n number of candy bars at the concession stand. So first, because I know we're going to be graphing this, I want to figure out which variable is my independent and which one is my dependent variable. So we know we're talking about the amount of money made from selling n number of candy bars. So if you think about it, the amount of money made is going to depend on how many candy bars I sell. So that means my amount of money is my dependent variable, and the number of candy bars sold is my independent variable. So this function is going to be linear because if you notice, there's nothing funky happening to this n. It kind of looks like slope-intercept form. And if it looks like slope-intercept form, remember that y equals mx plus b, then it is going to be a linear function. So we want to know what a reasonable domain would be for this situation. Remember, domain relates to your independent variable or what you can plug in for x. So because we're thinking about the number of candy bars that we can sell at the concession stand, I know that I can't sell negative candy bars because that doesn't make any sense, but I could sell 0 candy bars. But then I can't sell like a half a candy bar, so my domain is actually going to be discrete, and I'm going to have to only use whole numbers. So to show that this just continues on, you just put kind of like a dot, dot, dot. So then we kind of answer part C with our domain question. Because my domain can't have any fractions or decimals, this is going to be a discrete graph. So remember, discrete is dots when we draw it. So then we need to actually graph the function rule. So first we need to label our axes. We have number of candy bars sold. And then we have money made on the y-axis. So then to label that, we're just going to count by ones, make life simple. And then because we start at 3, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8. So we can count by ones, it's fine, or twos. I like twos better. 2, 4, 6, 8, 10, 12. All right, so to graph this, we know that if I sell 0 candy bars, I still have to plug that in. So 0 candy bars, 2 times 0 plus 3. This is coming from this function rule up here. Oops. Plus 3. That would give me A equals $3. How I'm making money without selling candy bars is a mystery to me, but please someone tell me. But then we do the same. So when we sell 1 candy bar, we would have 2 times 1 plus 3, and 2 times 1 is 2, plus 3 is 5. So then 1, 5, and then we would keep going up to and over 1 for every single one. And because this is a discrete graph, we're not going to be connecting these. They're just going to be individual dots like that. Okay? So for number 6, the function a equals negative 3n plus 7 represents the amount of water in a fish tank when n number of gallons is being removed. So my independent and dependent variables, we know we're talking about the amount of water in a fish tank with n number of gallons. So the amount of water in a fish tank is going to depend on the number of gallons that are being taken out. So my independent is number of gallons and my dependent is the amount of water. Looking at the function rule, it is going to be a linear function because it looks like it's in slope-intercept form. Remember, y equals mx plus b. Even though they're using different letters, it doesn't matter. It still has that same format where there's 2 numbers and 2 variables. So then, if we want a reasonable domain for this situation, if you think about water pouring out of a fish tank, first off, it'd be a huge mess, but you wouldn't be losing one whole gallon at a time. You'd be losing partial gallons all the time, half a gallon, quarter gallon, however much it may be, but it'd be a constant flow. So that means that my reasonable domain would be any x value that is greater or equal to 0, because if I didn't feel like taking water out, then I could take 0 gallons of water out. So because I can have partial portions of a gallon, that means that this can be a continuous graph. So then to actually graph the function rule, we have number of gallons on our x-axis, and then we have amount of water. So we have 7, so we can just count by ones on the axes. It'll be okay. 6, 7, and 1, 2, 3, 4, 5. Okay, so then to graph this, this 7 tells me that before I empty any water, I have 7 gallons in my tank. And then -3 tells me that I'm going down 3 gallons every, or I'm losing 3 gallons every time. So we have 3 and over, down 3 over 1, and then you just connect your dots. And whenever it hits the x-axis, you can just stop, because that means your fish tank is now empty, and hopefully you saved your fish. It's happened to me before. The fish survived. It was great. So for number 7, we are graphing these. And so we want to, first off, you should recognize this is slope-intercept form, which should automatically tell you this is with your y-intercept, and this is your slope. So we plot the y-intercept at -8, so 1, 2, 3, 4, 5, 6, 7, 8, all the way down here. And then from that point, my slope is positive 5 over 1, so I will rise 5, 1, 2, 3, 4, 5, and run 1. And then you just connect your dots. Oops, too far. All right, so then for number 8, we are going to go up 6 because my y-intercept is 6. And then we are going to go, because it's -3, 4, we can go down 3, right 4, or we can go up 3 and left 4. Notice my negative directions, I can't do both of them, just one. So we can go down 3, 1, 2, 3, right 4, 1, 2, 3, 4, and plot your point. And remember, a negative slope should be coming down and to the right, as if you were coming down a ski slope, like when you're reading left to right. Okay, so then for 9 and 10, these functions are both nonlinear, because you notice the x has extra stuff happening to it. And this, for number 9, that's a absolute value function. And then for number 10, that is also nonlinear, because that's a quadratic, because notice the x has a squared. So in order to graph these, you just have to make a table of values and solve. You can always use these numbers kind of as your basis: -2, -1, 0, 1, and 2. But when we plug this in, -2, and actually let me write it down here, negative absolute value of -2 minus 1 plus 3. -2 minus 1 is the absolute value of -3, and the absolute value of -3 is 3. So then 3 plus 3 gives me 6. So then I plug in my next number, -1. -1 minus -1 is -2. The absolute value of -2 is 2, and 2 plus 3 is 5. Okay, and then we take that number out, and we do it again. 0 minus 1 is -1. Absolute value of -1 is 1, and 1 plus 3 is 4. Oops. Then we plug in 1. Boop. Oops. And when we plug in 1, oops, see, I erased too much. 1 minus 1 gives me 0, so then I have 0 plus 3, which is just 3. And then when I plug in 2, I would have 2 minus 1, which is just 1. And 1, absolute value of 1 is 1, so then that would give me 4. So then you just plot the point, so -2, 6 would be up here. -1, 5 would go left 1, up 5. 0, 4 would just go up 4, because we can't go left or right with a 0. 1, 3 would be our next point, and then last but not least, 2, 4. So anytime you see an absolute value, it will always look like a V like this, but keep in mind that if it's been transformed at all, it might not be exactly near the center like this one is. Okay? So then for number 10, we can do the exact same thing. We're going to make a table of values, and we are going to plug in -2, 0, 1, and 2. So if we plug in -2, that would give me -4 times -2 squared. -2 squared is -2 times -2, which is +4. And +4 times -4 gives me -16. So then if I plug in -1, -1 squared is +1, and +1 times -4 is -4. Oops. Then we plug in 0. 0 squared is 0 times -4 is still 0. If we plug in 1, 1 squared times -4 is -4. And if we plug in 2, 2 squared is 4 times -4 is -16. So notice my graph is a little skewed. If you want, you can change the scale of this. And I think this is by 8s, 2, 4, 6, 8. Yeah, they're by 8, so you can count by 2s if you would like. So if I did that, 2, 4, 6, the top is 16. Then I would have at -1, 4, or -4, I'm sorry. So we'd actually be coming down. And then -2, -16 would be down here. And then with the parabola, it's going to look the same on both sides. And then you just do your best to make it look like a U at the top, like that. Okay? So now for number 11, the cost C of belonging to a climbing gym is $60 per year plus $4 per visit. In words, identify the independent and dependent variables. Well, independent variables, we have cost C because they give us variables. Those are your hints. So cost C, and we have a per visit cost as well. So because there's a per visit cost, that means my total cost depends on how many times I visit. So my independent variable is number of visits, and my dependent variable would be my total cost. So then, knowing that, I want to write a function rule that represents the cost of the climbing gym each year. So you want to use the same variables they have. Since it is your total cost, we know that the C is going to be by itself, and C is going to be your annual $60 per year plus that per visit fee. So since that $60 it has to be paid regardless, you are going to pay $60. It doesn't matter if there's a V with it because ultimately you have to pay $60. But then every time you visit, that's going to be another $4. So because of that repeated addition, that tells you it is going to be multiplication and just be 4V instead. So then if I want to know how much it will cost each year, if I want to go climbing 24 times, I am going to just plug in 24 for V. So 60 plus 4 times 24. Now this is where your calculator comes in handy. 4 times 24 plus 60. 4 times 24 plus 60 is 156. So this climbing gym would cost you $156 for the year if you went 24 times, which is probably not, I feel like that's kind of expensive, but maybe I'm just crazy. All right, so now for 12 and 13, we need to decide if it is a function or not. So remember, for it to be a function, you have to be able to draw a vertical line and only hit the graph once. So if you notice with this parabola, no matter how many vertical lines I draw, which I know that one was kind of wonky, but all of these vertical lines will only hit this parabola once. So because of this, that means it is a function. Yay! I don't know what kind of smiley face that was. There we go. Now, if you look at Mr. Smiley Face guy in number 13, though, When I draw vertical lines, notice I'm hitting more than one thing at a time. I'm hitting right here, I'm hitting here, I'm hitting right here. And that happens a bunch of times with this smiley face. So because I'm hitting more than once, this is not a function. So even though he looks like he's happy, he's not. So for 14, we want to determine if the relation is a function. And whenever you have these questions, you're really just looking at, do any of my x values repeat? In this case, we have -3, 1, 2, 0, and 2. So because these 2's are in common, this is not a function because x values repeat. So then, with number 15, if f of x is equal to the absolute value of x plus 2 minus 9, we want to determine f of -5. Remember, this function notation just means that you are taking wherever the x is and plugging it in with the number they want. So -5 plus 2 minus 9. -5 minus 2 would be -3. And the absolute value of -3 is going to be a +3. And so 3 minus 9 gives you -6. So then, technically, the correct way to write it is f of -5 equals -6. For number 16, if g of x equals 3x squared and h of x equals -7x plus 1, we want to determine g of -2 plus h of 4. So in order to do this, first you need to figure out what are each of these values. In order to get g of -2, you are plugging it in. So we would have 3 times -2 squared. Remember, -2 squared is a +4, and +4 times 3 is a 12. Oops. G of -2. There we go. So then we need to do the same except with h of 4. So we have h of 4 equals -7 times 4 plus 1. -7 times 4 is -28 plus 1 gives me -27. So then I have g of -2, which is 12, plus h of 4, which is -27. So really, I have 12 minus 27, which gives me -15. I didn't trust my mental math just now. Okay? For number 17, we need to figure out the domain of f of x. And so all we do is take each of these domain values, the -2, -1.5, 3, and 4, and plug them in. So starting off with -2, we would have 6 times -2 minus 5. 6 times -2 is -12, and minus 5 gives me -17. Then if I plug in -1.5, I have 6 times -1.5 minus 5. Now I know I don't know what 6 times -1.5 is. Boop. That is -9. And -9 minus 5, boop, is -14. So then, with 3, we are plugging in for x. So 6 times 3 minus 5. 6 times 3 is 18, minus 5 is 13. And then last but not least, we want to plug in 4. So 6 times 4 minus 5. 6 times 4 is 24, and that minus 5 is 19. So then my range is just these numbers in list form. So, whoop, range is -17, -14, 13, 19. Okay. All right. So now we are getting into our actual stats stuff. So we have 30 students from Air Academy High School were selected at random and asked their shoe size. The results of the survey are provided below. We are going to make a dot plot. So looking at female shoe sizes, we have ranging from 6 to 9. So I'm just going to have 5, 6, 7, 8, 9, 10. And boys, let's see, they go up to 11. So actually, we'll go up to 11 since they do. 11, 9, oops, 8, 7, 6. That way it'll be easier to compare them if we need to. So for females, we have, let me make my pen a little bit bigger, but we have a 9, 8, 6, 7, 7, 8, 9, 6. Ah, man. We're just going to extend this a little bit. I didn't notice that 5. Dang it. But the 5, and then the 7. Boop. And then another 8, another 6, another 8, and then 2 7s. Boop, boop. Oops. Don't want it that close. Okay. There it goes. All right. So then to do the boys graph, again, I got to make the pen thicker. We have 11, 7. Oops. Actually, the bigger. There it is. All right. So 11, 7, 10, 9, 6, 11, 8, 7, 11, 8, 7, 9, 11, 10, 8, 9, 11, 10. So 8, 9, 11, 10. All right. So now that we have these drawn, now we can use that to answer the questions about these dot plots. So let me put these back to normal size. So if we are looking at the female shoe size and its distribution, for the most part, even though it's kind of low on the left side, it is pretty well symmetrical, I would say. So we can say symmetrical. Words are hard sometimes. And so if I have a symmetrical distribution, that means my measure of center I want to use is always going to be mean. Now, if I needed to calculate the measure of center, this is where your handy dandy calculator comes into play. So if you hit stat, you can edit those lists. Remember, if you need to clear it out, you just go up to the top, and hit enter. And then you go over to the L1, clear, and enter. So you can just enter the data as you see it. 9 plus 8. What am I doing? Not 9 plus 8. 9. I was thinking of doing mean in my head. 8, 6, 7, 7, 8, 9, 6, 5, 7, 8, 6, 8, 7, 7. And then we'll go over to the next list and just enter those now since we're already at the screen. 11, 7, 10, 9, 6, 11, 8, 7, 9, 11, 10, 8, 9, 11, and 10. So, hit the table. So now to calculate the measure of center, if you hit your stat button on your calculator, remember you need to have a graphing calculator with the test, but you hit your 1var stats and you tell it what list you want. So since we are doing females, we're just going to calculate our mean with that. And remember, mean is the little X with the bar. So in this case, my mean is going to be 7.2. So now looking at the males, the shape of the males is that it looks like it's skewed. There's more data on the right side and less data on the left. So since there's less data on the left, this is going to be skewed left. So then if I have a skewed distribution, that means I want to use median in order to find my typical shoe size. So in order to calculate median, we do the exact same thing we just did. You hit stat, you write over to calc, you hit 1var stats. But instead of L1, make sure you tell it you want L2 because that's where my boys list is. Enter, enter, enter. And with your 1var stats, you can scroll down and your median is going to be that MED. So median for boys is 9. So then looking at the standard deviation for the boys is 1.64. Oops, can't write. And then for the girls, standard deviation, and you can do it real quick, stat right over to calc, hit one var stats, tell it that you want list 1, enter, 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 and standard deviation, that S of X for girls is 1.15 because that 6 tells us to round up the 4. So it looks like males have a higher standard deviation, and this means that looking at the shoe sizes, male shoe sizes vary more than females. So male shoe sizes vary more than females. Okay. So for number 19, we need to do a 5-number summary. So you're going to come back to your list. So you're going to hit edit, and I'm going to clear out my list because I am done with them. Boop, boop, boop. Clear. So for this marine biologist, we have 28, 52, 32, 48, 27, 86, 14, 55, 22, 30, 50, 36, 24, and 38. So make sure, by the way, I didn't mention this before, but make sure you check to that your data is entered correctly. But to get the 5-number summary, you hit stat, you write over to calc, and you do your 1 var stats again and enter, enter, enter. And your 5-number summary, if you scroll down, are these 5 numbers right here. So you have your, come on. We have our min is 14. Our Q1 is at 27. Our median is at 34. Our Q3 is at 50. And our max is at 86. So because we want to draw a box plot, we're going to have to be able to go from 14 to 86. So I'm thinking 10, 20, 30, 40, 50, 60, 70, 80. Perfect. So we're going to have 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So in order to draw this box plot, you are just estimating 14 is my minimum. So I'm going to put a dot. Then my Q1 is 27. So I'm going to come, and this time I'm going to draw a line because this is a part of my box. For median at 34, again, it's a part of the box, so draw a line. And then for Q3, it is also a part of the box. So you have all parts of your box plot. And then for your max of 86, you just connect it to the box like so, and you connect your other side if you didn't already do that because I almost forgot. Oopsie. But this is the purpose of a box plot because remember it breaks it into 25% for each of these little sections in it. So looking at the distribution of weights, I would say this is skewed right because there's less data on the right side of the box plot. So then thinking about what percent of catfish weigh less than 27 pounds? Well, come back up to your 5-number summary because 27 pounds is your Q1. Which means if you want the percentage of what weighed less than that, you start at your 27. And notice I only have one little section of this box plot, which means that's only 25%. So it's not very much. Now, the heaviest 50% of catfish weigh more than what weight? Again, each of these sections is 25%. So that's 25%. That's 25%. So if I want the heaviest 50%, I need to look at my median. My median is 34, so the heaviest 50% are heavier than 34 pounds. Okay? Now, last but not least is estimating outliers. Remember, that just means it's really far, it's either really big or really small. So looking at the catfish weights, you can kind of tell just from the 5-number summary of 14, 27, 34, 50. Those are all pretty well spread out, but they're kind of close. But then it all of a sudden jumps to 86. So I would say 86 is our outlier. So then to calculate the mean and standard deviation of the catfish weights, you already have it. That's your 5-number summary. Just come back up. My mean is going to be that X with the bar, which in this case is 38.71. And then my standard deviation is at SX, which is going to be 18.35. Okay. So now for number 20, we have some elementary school students who are being surveyed for their favorite colors given red, yellow, orange, and green. So we first need to fill in the table. So looking at this, we know we have 450 students and 250 of them were females. So if I subtract 450 minus 250, that tells me that I have 200 males total. Now, if I have 200 males total, now I can subtract all of the other colors so that I can find red. So 200 minus 54 students that like green, minus the 32 students who like orange, minus the 67 who like yellow. That gives me 47 students who liked red. So then for females, we know we have 222 of them. But then we need to find how many like yellow. So we subtract what we know. 85 of them liked green, minus the 112 that like yellow, or oops, misread that, my bad. Minus the 66 that like orange, minus the 26 that like red. Okay, so we're looking at that second row. And when I do that, I find that 45 females like the color yellow. So then to finish this off, we just have to do 32 plus 66, which gives us, oops, it didn't hit the plus sign. 98. Yay. So then we want to know how many more females than males chose the color green. Well, we had 85 females compared to 54 males, so 85 minus 54, not 34, 54. There we go. Gives us 31 more females. So then, how many more males chose the color red than yellow? We are looking at red and yellow. With this, we would have 67 minus 47, which you might be able to do in your head, is just 20. So 20 more males. Oh, wait. How many males chose red rather than yellow? Well, technically, more males chose yellow. So I'm just going to say more males chose yellow. Oops. All right, so then, is the data value 66 a joint or marginal frequency? 66 is right here, in case you didn't see it. And so because it is where two traits overlap, this would be a joint frequency. So that tells you that 66 of the 450 were females who liked the color orange. Now, if the data value 228, that one, let's see, 228. I'm going to assume that's supposed to be a 222. One of our total rows at least. Ooh, that's bad. And because it is in the margins, that would be marginal frequency. Okay. So to make a relative frequency table for this, you just take your top or your numbers that you have up here and divide them by your grand total. So for red, I would have 47 divided by 450, which gives me 10.4 or 0.1044. So when I move that, that would be 10.44%. So then for yellow, with yellow, we have 67 out of 450, so 67 divided by 450 By the way, if you're not good at moving the decimal in your head, you can also just multiply by 100 once you have that decimal. And we get 14.888. So that third 8 tells us to round it up. So it is 14.89%. So then for orange, we have 32 divided by 450. And 32 divided by 450 is going to give us 7.11%. And then for green, we have 54 divided by 450. I can type faster than my simulator can handle. So that gives me 12% for green. And then we have our totals, 200 divided by the grand total, which is 450. And some of you may have noticed that these numbers don't add up quite right. So we have some editing to do, unfortunately, but it is okay. But we have 44%. So then with that, with females, we have 26 out of 450. So 26 divided by 450 gives us 5.78%. To get my yellow, we are going to get 45 minus 450, which should be, I want to say 0.1. Oops. 45 divided by 450. There we go. And 45, oh, there we are. Yes, it is. So that is 10%. Then we have 66 divided by 450. And some of you I know are just annoyed with calculator work. It is all good. It is almost over. That gives you 14.67%. We do it again. 85 divided by 450. That gives us 18.89%. And then 222 divided by 450 is 49%. And then last but not least, our final row, the last row. Good job being persevering, because I know this can be rough sometimes. That gives us 22.44%. Then we have 112 divided by 450, which is, as it loads, 24.89. Then we have 98 divided by 450. And that is 21.78. And then we have 139 divided by 450, which gives us 30.89. Of course, Microsoft would change color. And then last but not least, this one would just be 100%. And I know the numbers are messed up in the total columns here, so don't worry about it too much. So with all this being said, we want to know what the joint relative frequency of the number of males that chose green. So looking at this, males who chose green would be right here in this box. So that would mean that 12% of the people that participated are males who chose green. So then the marginal relative frequency of children who just chose the color yellow, we just look at the total for yellow. That's 24.89%. So 24.89%. And voila. Okay. So for number 21, this is our last one. Whoop, whoop. So we need to put this data into our list. So we come to our edit and we go up to our list name and we just clear it out for ourselves. And we have to enter this data. So we have 0, 5, 10, 12, 14. Now, remember when you are doing this, you have to put them in the same order that you see them. So 7.58 has to be with the 0, 8.57 has to be with the 5, and so on. But you enter all of the data into your calculator Again, trying and making sure that it is entered accurately, because if you mess up your number once, it will just mess you up completely. So in order to make a scatter plot of this data, this would be my, let's see if it cooperates. Years since 1990. So the x-axis is going to be the years since 1990, and my y-axis is going to be my hourly earnings. Now you're going to have to scale this a bit since it goes up to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we can count by 2. So 2, 4, 6, 8, 10, 12, 14, 16, blah, 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 blah. And then my other one goes up to 11. So that is, let's see, I can count by 2s again. So 2, 4, 6, 8, 10, 12, 14, 16. So when we plot these points at 0, we're at 7.58. So we're about here. Then at 5, we are at 8.57. So you're kind of estimating, but getting a rough picture of what it looks like. At 10, you're at 10, approximately. At 12, you're a little bit higher. And then at 14, a little bit higher still. But still not quite making, just over 11 at least. So then with this, we want to get a line of best fit. So to get your line of best fit, you're going to hit stat. You're going to write over to calc. Oops, too many times. And then you're going to go down to where it says linreg, or you just push the number 4, kind of up to you. But when you hit that, you enter the list that you put your data into, whichever ones you chose. And then you should see this R at the very bottom, that 0.997. Since, oh wait, sorry, that's the correlation coefficient. Ooh, that's going to be later. But for my equation of best fit, I have this y equals ax plus b, and I have a and I have b. So you just have to plug it in. Y equals my a value, which is 0.256, which would just be 0.26x. And then my b is 7.46, so plus 7.46. So then we want to identify the slope that we found. So in part B, my slope is just the 0.26. So in this case, this means that your hourly earnings would go up by 0.26 or 26 cents for each year since 1990. So wage increase 26 cents per year since 1990. So then, identifying the y-intercept of this line of best fit, we're looking at that 746. And in this problem, thinking about it, it does make sense that the hourly earnings was 746, because back in 1990, the minimum wage was much lower. And honestly, there's still plenty of states that their minimum wage is the federal minimum wage, which is $7.25, unless I'm super outdated. Let me know if I am. So this does make sense in the problem, because that would be $7.46 an hour. Okay, so looking at the scatter plot and the line of best fit, we want to just kind of sketch it on there. So because it's at 7.46, I'm going to put a little dot, and I have to go up by 0.26, so it's just going to be, just kind of estimate, it would look something like that. And your graphing calculator can do it. You have to hit alpha trace. Ooh, it might be too late to do this. Yes, it is. Oopsie. So you can just type this in if you hit your y equals, though, and it will graph it on a graph for you if you want. So now, using that equation of the line of best fit, we want to figure out or predict the average hourly earnings in the year 2002. Since X is the number of years since 1990, that means I'm actually going to plug in 1990 2000 is 10 years plus 2 more is 12. So that would be y equals 0.26 times 12 plus 7.46. So 0.26 times 12 plus 7.46 gives us 10.58. So that means by 2002, it's approximately 1058. So then my correlation coefficient, this is what I got almost told you about earlier, but you hit stat, you write over to calc, you can hit 4 or you can scroll down, but when you go into your enter, PS, if you want to use that Y1, you hit alpha trace Y1 right there. But then you come down to calculate, and when you hit it, your correlation coefficient is at 0.99. So since it's 0.997, looking at that 9, the 7 tells me to round up. So this is a correlation coefficient of 1. And if you have a correlation coefficient of 1, that is a positive, perfect positive linear relationship. So your conclusion would just be this sentence exactly as you see it. Now, that is the end of this midterm review for Algebra 1. I hope you found it helpful. If you did, give it a like, subscribe to the channel so that you get notifications when new videos are made, and so that you can see more math awesomeness. If you have any questions, just comment below, and I will see you guys later.